So now we can do basically any application involving solving a triangle. Doesn't have to be a right triangle. It can be anything. So we're just going to do two problems. The first one relates to navigation. So just follow along with me here. Two boats leave a port at the same time. One travels north 50 degrees east, and I want to explain what that means. So north 50 degrees east means 50 degrees east of due north. So due north points up, and then you go 50 degrees east of that. So that's going to look like this. You don't have to have that fact memorized. It's just something we use for navigation. So that angle's 50. So rather than just saying northeast, now we can be a lot more specific. We can mean 50 degrees east of due north. Okay. So for 30 miles, and the other boat travels south 70 degrees east. So that's the same exact thing. 70 degrees east of due south is just going to end up looking like that for 26 miles. Right. Boat 1, boat 2. So we want to know how far apart are they now. Okay. So this is a problem involving a triangle. It's not a right triangle. The way I've drawn it almost kind of looks like it might be, but it's not. And we can't just assume things. So the thing we want to know is this dotted line. Now we have that and that. That's 30 miles and that's 26 miles. So a good way to look at these is just to completely divorce it from what we're even talking about and just draw it as a triangle and then just see what information you need and then figure out, okay, am I using law cosines or law sines or what? So if you just draw it as a triangle, it looks like that. That side is 30, that side is 26. And the problem we have here is we don't have any internal angle from this triangle. Right, we don't have any of these angles. We want this side, but we need some more stuff. So if you look back at the original diagram with just a little bit of like intuitive geometry stuff, we can get it. This is 50 degrees, this is 70 degrees. We want this. So if you think about these three angles, 1, 2, 3, they have to add up to 180. Right, because this is a straight line, this is 180. So this angle plus this angle plus this angle has to be 180. So to get this internal angle, which is this, right, we need something. We just do, I guess we should probably label it. Let's label the sides of our things. Well, let's say label side A the thing that we want. Okay, and that way angle A is the thing that we're about to get. And then, well, we'll see what else we have to do. We don't really care about these angles, right? We don't care what these are. So this is the one we care about side A, and right now we can get angle A. So angle A just turns out to be 180 minus 50 minus 70, which is 60. Okay, so we weren't given that information, but it didn't take a whole ton of work to get it. Okay, so now we just have to think about what we need to do. We have this angle, this is 60 degrees. And really, with these problems, the thing to think about is this. Do I have any side in their corresponding angle? No. I have this angle, but not this side. I have these two sides, but I don't have these angles. I don't have a way to get these angles. And furthermore, I don't really need them. You're not being asked to solve this triangle. You're just being asked to solve this one side. So that's it. So do I have side in the corresponding angle? No. I have to use the law cosines. Right? I cannot use the law sines if I don't have that. So really that's the most general way to think about which one to do. Okay, and if you think about this, this is just like a straight up law cosines thing. You want this side, you have the other two sides, and you have this side's corresponding angle. So that's just the first, what we would call the side version of the law of cosines. I'm erasing the side. So a squared is 30 squared plus 26 squared minus 2 times 30 times 26 times the cosine of 60. I don't know. Okay, and I should make a note. Well, that's the law of cosines, right? What else would it be? So we eliminated being able to use the law of sines, and we have to do the law of cosines. Okay, so from here, that's just calculator stuff. That actually turns out nicely to be exactly 796. Sometimes that'll happen. Why would that happen? Because the cosine of 60 degrees is actually 1/2. So that works out. And then don't forget you're not done. And again, I would hope that you would think, okay, if this is 30 miles and this is 26 miles, this isn't 796 miles, right? That's too big. So A is the square root of 796. Which is about 28.21 miles. Okay, so sometimes you're given all the information you need. Sometimes you're missing one little piece of information like we would with this angle, and we just kind of use some basic intuitive geometry stuff to figure it out. All right, let's follow along with me. The angle of elevation to the peak of a mountain is 32 degrees. So you measure your angle of elevation to the peak to be 32 degrees. 1,000 feet closer along a flat plane, so you walk 1,000 feet, right? We're assuming along a flat plane, and then you take a measurement again. The angle of elevation is 35 degrees. Should make sense. The closer you get, you have to look up a little bit more to look at the peak. How tall is the peak? So this one, believe it or not, takes a little bit of doing, but this is the point of trig in the first place, is to measure stuff that you can't possibly measure just using things like angles. Okay, so we draw a picture. Here's us at our first initial point of measurement. Here's our flat plane. And we said, okay, from our first measurement to the peak looked like 32 degrees. So let's say this is the peak of a mountain. Now, we can't just walk up to the base of this thing. It's not a sheer cliff. If it was, then we could just, then this would be a right triangle. But that's not very realistic anyways, right? So now we're saying, okay, that's 32 degrees. We walked 1,000 feet. So let's say we walked to here. Took another measurement to the peak. And we found that to be 35 degrees. And then the only other measurement we have here is that the distance we walked between here and here is 1,000. All right. So the thing we really want, so this is all the information we have. The thing we really want is actually this. Right. We want the physical height to the peak. So there is a right triangle in here, right? The problem is just that the leg of the right triangle we want is right down the middle of this mountain, and we can't get to it. So we're going to have to do a little bit of fussing around with these oblique triangles, well, this oblique triangle, to get some more information about this right triangle, which we can then use right triangle stuff to hopefully get this. So let me make a note there. That's a right triangle, right? And that's something we can know a lot about as long as we know anything else about it. We don't know this leg, we don't know the hypotenuse, and we need to know this leg. Okay, so there's not just one way to do this. Here's what I'm going to do. I'm going to find this. I'm going to find the hypotenuse of the right triangle, the smaller of the two right triangles, right? There's actually two right triangles here. There's this smaller one and this bigger one. I'm going to get the hypotenuse of this smaller one. And I'm going to do that based on the fact that I know a little bit. This skinny oblique triangle over here is the only one I know anything about. So like the only side measurement I have is this 1,000. So I better get one of these other angles in this triangle. So what I'm going to do is I'm going to get this one so that I can use the law of sines. Since this is the only side I can possibly have at the moment, I must have to get an angle and I must have to use the law of sines. Law of cosines, you always need a couple sides. Okay, so I don't know this angle, but again, let's just completely divorce it from context and just set it up as a big triangle. So it looks like that. There's our bigger right triangle. There's our smaller right triangle. That's 35 degrees, that's 32 degrees, and that's 1,000. That's better. Okay, so I want this angle, this small angle up top here. I only really have one other angle right now, but I can very easily get this angle because the same kind of thing as the last problem. This angle and this angle are supplementary, which means they have to add to 180 degrees. So to get this angle, whatever we want to call it, we're gonna we're gonna do 180 minus 35. So we better give it a name, shouldn't we? Well, not really. I don't really care. I want this angle. So this angle here is 180. I'll just label it what it is. Minus 35, which is 145. That's it. That's all we're going to do with this piece of information. This 35 degree gives us this 145 degree. So that means the skinny angle up here, right? This, and this have to add to 180. So the little angle up here is 180 minus 145 minus 32, which isn't much, is 3 degrees. Obviously my picture is not to scale, but it involves a mountain. They're big. What do you want? So that is 3 degrees, even though it doesn't look like it in my picture. All right, you're going to forget about the mountain for now. We need this. I'm going to now get this, the hypotenuse of the smaller right triangle. And, the reason I wanted this one again is so I can use the law of sines. This is the only side I have, so I need its corresponding angle. So let's do it. Sine of 3 degrees over 1,000. Now, you could pull this problem off by finding this other hypotenuse here as well. It would essentially work out the same way. So this isn't the only way to do it. Again, I'm finding this thing equals, so let's see, let's call this since this is the hypotenuse of a right triangle, let's call this side, let's call this side C. Sure, right, because it's opposite this one. Yeah, that'll make it a little easier. So equals sine of 32 over the thing we actually want, C. All right, so the sine of this angle over 1,000 equals the sine of this angle over whatever this side is. And see what I'm saying? This side is going to become the hypotenuse of the right triangle, which is going to give us this side, which is the thing we want. Okay, so we've done this type of thing before. We're just gonna, you can think about it as cross multiplying. Let's actually cross multiply. So C times sine of 3 equals 1,000 times sine of 32, which means that C is 1,000 times sine of 32 over sine of 3. That's a pretty quick way to do these little law sign problems. Which calculator time? This is a big number, these are small numbers, but sine of 3 is a very small number. So this turns out to be, C turns out to be 10,125.34. Okay, so we had to do a little oblique triangle stuff, law signs, to get that. Once again, well, let's just label what we have and what we need now that we have like our final missing piece of information. We know that's 35 degrees. So this is the smaller of the right triangles. This is that thing. That's the mountain. We want that. And then we have that this is 10,125.34. So it's like we had to get a useless piece of information to get a useful one. This 10,000 number is the distance where if you could fly straight to the top of the mountain, that's the distance, but you can't fly. So really this number doesn't mean anything, but it is a means to an end because it gets us this. It gets us the thing we want. Okay, so now we just think, okay, I have an angle and a triangle. I need the opposite side. I have the hypotenuse, O and H. Which one of the three right triangle thingies is O and H? It's sine is opposite over hypotenuse. So sine of 35 degrees equals op, the thing you want, over 10,125.34. Which means that op is, I would just think about this as, so we're solving for op, multiply both sides of the equation by 10,000, blah, 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 whatever. 10,125.34 times sine of 35. I like to do little asterisks instead of just dots when you're multiplying if your problem involves decimals, because or else it gets sloppy looking. As long as you remember what you were doing. Okay, which, you just have to take my word for it, turns out to be 5,807.66 feet.